Okay, so today we'll be going over space curves. These are curves in three-dimensional space. We're going to start with some two-dimensional ones. A lot of the problems in y'all's book, they specifically state program it into MATLAB and look at the problems that way. But we're going to see, can we actually just look at some parametric equations and try to figure out what they actually look like, okay? So, let's start with, okay, so this is saying x, y, and z. I'm going to start with a parametric equation that's only in two dimensions. So let's say r of t is going to be represented by negative cosine of t and t. Okay. Now, when you first start thinking about this problem, one of the things you want to think about is what are the boundaries associated with the x direction, okay? So, with negative cosine of t, it doesn't matter that it's negative. Negative cosine of t is always going to be bounded between -1 and 1. No matter what, it's a wave, that's what it is, okay? So, whenever you're doing a problem like this, what you want to do is think that the y variable is your t. So we're going to start sampling t points and see if we can't figure out what this thing actually looks like. All right? So let's begin at the start and say, what is r of 0? Well, cosine of 0 is 1. But this is negative cosine of 0, so that's going to be -1, 0. Okay? And then let's say, well, what would r of pi over 2 be? Okay, now cosine of pi over 2 is 0, so this would be 0, comma, pi over 2. Okay, and I'm going to start plotting, these are vectors, but I'm going to start plotting them at this points. Okay, so this first one is just going to go right here. So that's -1, 0 right there. Okay, and then if I shift over to this guy right here, that's going to be 0, comma, pi over 2. So that guy's going to appear right there. What if I tried going down? So let's say r of negative pi over 2. Well, that would be 0, comma, negative pi over 2. So I would end up with a point that would be somewhere down there. Okay, so I have 0, negative pi over 2. And let's say, I said, what is r of pi? Okay, now cosine of pi is -1, but this is negative cosine of pi, so the negative and the negative will cancel each other out. So that would be 1, comma, pi. And so that point would be, okay, it'd be shifted over by 1, and it's going to go up to this point of pi, right here. Okay? So t is changing in the y direction, but the x direction is corresponding to negative cosine of t. So if I think about what is the type of shape of this graph that I'm dealing with right here, okay, so this is going to have to correspond to the cosine wave, but inverted because it's negative cosine of t. Okay. And it's going to have to pass through that point right there. Okay, so, and remember, at the beginning of this one, I said cosine is always going to be bounded between -1 and 1. That means that the x direction is going to be bounded between -1 and 1. Okay, so it's never going to go out in the x direction beyond -1 and 1. But t can grow in the y direction in either direction. So what do we end up with? We end up with, this is obviously not a function because it doesn't pass the vertical line test. But, you know, we end up with cosine basically just going up in the y direction because we're telling the y direction it's t. It can grow and shrink, but the cosine wave itself is going to be bounded between -1 and 1. So to try to get an idea of these curves, you want to say, well, why don't I sample some points and try to figure out what this thing would actually look like? Okay. All right, let's try another one. Let's say r of t is going to equal 3 sine of t 2 cosine of t. Okay, once again, this thing is two-dimensional. So, this one is not that obvious of what this thing would look like. But what we're going to do is we're going to sample the standard points. We'll say, what is it at 0? What is it at pi over 2? What is it at pi? 3 pi over 2, anything like that. Okay? So let's say, okay, I'll start out with, let's say r of 0. Now sine of 0 is 0. And cosine of 0 is 1, but it's 1 times 2, so that's going to be the point 2. Okay. So let me just start this guy off. Okay, so 0 in the x direction, and then up by 2 in the y direction. Okay. Let's go to our next spot. Let's say, what would r of pi divided by 2 equal? Okay. Well, sine of pi over 2 is 1, but that's going to be 3 times 1, so that's going to be 3. And cosine of pi over 2 is 0, so that's going to come out to 0. So we'll go over here. 1, 2, 3. Okay. So I'm going to put that point right there. All right, let's go to our next standard one. Let's say r of pi. Okay. Now, sine of pi is going to be 0, and cosine of pi is -1. So, this will come out to 0, -2. Okay, so now I'm down 1, 2. I guess this point right here. Okay. And now let's say, well, let's go a little bit further. Let's say r of 3 pi divided by 2. Okay, now sine of 3 pi divided by 2 is actually -1. So that would be -1 times 3. So that would come out to being a -3, 0. So I'm going to go back 1, 2, and 3. We'll put that guy right there. Okay. Now, if I went to the next point, r of 2 pi, what would I end up getting? If I plug 2 pi into this thing, sine of 2 pi is 0, and cosine of 2 pi is 1. So I get back to the point 0, 2. So I would get back to this point right here. So what is actually the curve that we're looking at that is represented by these parametric equations? We're looking at an ellipse. Okay. And we're looking at an ellipse because sine is being multiplied by 3. Well, we're going to have a 3 in the x direction, and cosine is being multiplied by 2, so we're going to have a 2 in the y direction. Okay. And it doesn't actually do this in your book, but if you want to think about it as a trajectory, you start traveling around this way, and this way, and this way, like that. And so this is big. Oh, I'm trying on the wrong piece of paper, sorry. So as t grows with time, this is just going to be an ellipse that is going to circle around in this direction. Okay, so that's a couple of examples in a two-dimensional one. Let's ask a question about a three-dimensional one. The three-dimensional ones they're actually pretty tricky to draw. But let's say, what if we trapped one inside of a plane? Okay, so let's say, let's find an equation of the plane containing a curve. All right, so we're going to say R of t, which is going to equal t, 4, t squared. Okay, so now we're talking about something in 3D. Okay. Let's go through the same process and ask ourselves, what are we sample points just to begin to try to understand what a curve like this would actually look like? Okay. So let's say 1 is R of 0. 0, 4, 0. Okay. Well, R of 1 would equal 1, 4, well, let's say 0 squared, 1 squared. Okay. And then we can say, what would R of 2 be? This would be 2, 4, and then 2 squared, which would be 4. Okay. Let's go in the opposite direction. Let's say, what was R of -1? This would be -1, 4, and then -1 squared, which is just 1. And then R of -2. That would be -2, 4, -2 squared, which would be 4. So we have to ask ourselves, all right, so the question stated that we want to find the equation of a plane that is containing this curve, and then we want to try to sketch this guy. Okay, so what is common between all of these points that we've been sampling? Well, the common thing between all of these points is that they all have y which equals 4. The plane that it passes through is y which equals 4. So if I try to sketch this thing, I know that it's going to exist within this plane. So the plane is y which equals 4. Okay. So draw this guy. Okay, remember, this direction is x. This direction is y, and this direction is z. All right? So I'm going to go out 1, 2, 3, and 4. Okay. So I know everybody has to be trapped within the plane y which equals 4. All right? And now I'm going to look at my x and z values and notice that I have t and t squared. Okay. So in the x direction, we're just going to have our t's. But in the z direction, we are going to have t squared. So what is this going to represent? Quadratic. The quadratic trapped within the plane y which equals 4. It's just a basic quadratic too. So what this guy end up looking like? You come down. This will look a little bit funny because I'm trying to draw three-dimensional things. Sort of like that guy right there. Yeah, guy right there. Okay. So this becomes a quadratic parametric equation just trapped within the plane y which equals 4. sometimes when talking about space curves, they're not always given as parametric equations. So the question becomes, how can we take a surface within a three-dimensional space and actually turn it into a parametric equation? Okay? So these things can be represented in different ways. So let's try one of those. So instead of given a parametric equation, let's say, let's find the parametric equation. For, let's say, z, which is going to equal the square root of x squared plus y squared. And z, which equals 1 plus y. Now z squared, which equals x squared plus y squared, is going to represent one of the surface, and z, which equals 1 plus y, is going to represent the other surface. Okay. And we're going to try to find the intersection of these two surfaces and describe it as a parametric equation. So how are we going to do this? Well, whenever you want to create a parametric equation, look, there's infinitely many of them that you can do. The easiest way to actually start a problem like this is to just let one of your variables just equal t. Okay, because remember, you have x of t, y of t, z of t. Well, pick one of them. Okay? So I'm going to let x equal t. Okay? So what is that going to give me if I just decide x equals t? Well, it means that z is going to equal the square root of t squared plus y squared. Okay, so that's not exactly what we want at this point. We want to say, well, I want y to also be a function of t. So we're looking for x as a function of t. We just decide x equals t. Okay? And now I want to look at this problem and I would say, okay, how do I find y as a function of t? Well, I have two conditions. I have this condition right here and this condition right here. So what am I going to do? I'm going to replace this z right here with 1 plus y. And then I'm going to solve for y as a function of t. And once I have solved for y as a function of t, I can then solve for z as a function of t. Okay. So just plugging this problem into this problem right here. What's that going to give me? That's going to give me, no, I'll put it right here. First we have this, and then we can say, you know what? 1 plus y would equal the square root of t squared plus y squared. Okay, now I can take this thing right here and I can manipulate it until I find y as a function of t. And once I have y as a function of t, I can plug that y back into this one right here to get z as a function of t. Now I'm giving my three parametric equations. So to do this, the first thing I'm going to do is I'm going to square both sides of this thing. So that would give me 1 plus 2y plus y squared is going to equal t squared plus y squared. All I'm doing is I'm squaring both sides of that problem. Okay? And then let's subtract y squared from both sides of the problem. That's not an issue. And so I get 1 plus 2y is going to equal now t squared. Right? And at this point, it's just algebra. We can solve for y. So if I subtract 1 and divide by 2, y is going to equal t squared minus 1 divided by 2. All right. So I have the first parametric equation, which equals t, and then I have my second parametric equation that y as a function of t is equal to t squared minus 1 divided by 2. Okay. Now I need to find z as a function of t. And so z equals 1 plus y. So z is going to equal 1 now plus t squared minus 1 divided by 2. All right. Now if I simplify this thing, this is t squared divided by 2 minus 1/2 plus 1. All right, negative 1/2 plus 1 is going to turn into a positive 1/2. And so z is going to equal t squared plus 1 divided by 2. Okay? So from this right here, this gives me that my r of t is going to equal now t comma t squared minus 1 divided by 2 comma t squared plus 1 divided by 2. And so given these x, y, z relationships, this is how you would actually get to a parametric form of this. And so how do we begin a problem like this? Let x equal t. Is this unique? No. I could let y equal t and try to solve from there. And I would end up with a different parametric equation. But the main difference between the two different parametric equations is just that your points in space lie at different points in time. Okay? So this is the parametric equation that is formed by that relationship. You might want to pay attention to this one. That appears on the number. Something similar.